now we are back in the second part of this process of creating a classification model using the ASHRAE Thermal Comfort Database 2 data. We have created a data frame of features that have one hot encoded the categorical features. And we also have a target data series that we can feed into our model. This time, instead of using manually creating train tests, we're going to use the train test split function from scikit-learn to split our target data set and create a test data set size of 30%. And you can also specify a random state. So if you wanted to replicate this, you could do that by specifying that. That's a little bit more of an advanced feature. Don't worry too much about it. As I simulate that, what you end up with is a features training data set that has 103 columns, 5 rows, because but that's just what it looks like. But if we look at .info, we have a features training data set with 30,684 rows and a features test data set with 13,000. It's automatically gone through and randomly divided the data set into train and test sets so that we can then use it to make our classifications. In order to get started of training our model, what we're going to be doing is creating a variable, which is going to be an object that is basically developed using the random forest classifier function from the scikit-learn library. We're going to specify we want out of bag score to be calculated, which you'll see here in a second why that's important. We're automating some of the attributes. Max features is an attribute, which we're going to allow the classifier to create itself. I won't go into detail about how the random forest classifier works, really, because that will be a big focus of future sections. Number of estimators will set a default minimum leaf sample and the random state again at 2. These are attributes, like I said, that you can dive into and learn a lot more about what they mean. This is really just the default parameters that we're setting, or default settings for these attributes, so don't worry too much about that. So we'll go ahead and create that object and we will fit the model. So now that we've done this, instead of like we did in the regression, basically running a test on our data set, what we can do is understand how the algorithm works using what's called out-of-bag error calculation, which is used in classification to understand how the model performs. And random forest is very specific in that it has this attribute. And what it's doing is it's basically calculating the error score using cross-validation on the inside. So taking train test data sets and running it over and over until you get a certain number of values, which you then average to create the accuracy. And the model accuracy that we're seeing from this trained model is almost 50%, which maybe seems low. Maybe it seems low that our model is only able to predict 50% of the time. But please keep in mind, this is a 7-class classification problem. So it's not binary. It's not yes or no. It's what class out of 7 different classes. So picking 50% correctly, is that a good thing or a bad thing? So what we need to do is create a baseline model to test have something to compare this 48.4% to. And we can do what's called a dummy classifier. And a dummy classifier is a model that picks the category simply based on random guessing, based on the probability that if you randomly guessed, you would get the class right. So using the dummy classifier, the model accuracy is only 28.9%. So comparing the baseline of 28% to our model of 48.4% shows that it's 20% better in terms of accuracy, which is quite a bit better. So accuracy is not the only thing that really matters for classification. And within random forest, there's also what's called a classification report, which allows you to see other metrics like what metrics called precision, recall, F1 score, and support metrics. And these metrics are helpful based on what your objective is. Are false positives or false negatives more or less important? And so I don't want to dive into these metrics today, but just know that there are other ways to score this. And you also can look at the different classes individually to understand how well the model is performing on it. And the overall score is close to 49%. Precision, recall, F1 score are all slightly different. We're not going to get into the details, like I said, of what these are, but that is the overall, 49% is the overall accuracy. But then you can also look at the accuracy on a class by class basis. Another cool thing about random forest is you have a function called feature importance, which is really telling you what was the most influential features when it came to helping to predict the right classification. And so you can calculate them using the feature importance function. If we rank all of the feature importances coming out of this model, you can see that air temperature, relative humidity, and air velocity are the most powerful predictors of comfort. So we can plot that. Let's just see what that looks like. And you can really see the magnitude of importance. So air temperature that the person is exposed to is by far the best input variable, as compared, not by far the best, but it is the best. Relative humidity is the second best. This is very intuitive. Whatever conditions the person is exposed to are having the most influence on an accurate prediction. Air velocity is great. It is also in there. Clothing level, metabolism. Year, for some reason, pops in there. We're not sure why that is. The sex, male versus female, the different seasons are also predictors that have a certain amount of importance, but not quite at the level as some of these others. So if the thermal comfort models out there are really dependent on these top 5 attributes, and it really the data really shows that is a good thing in a sense, because they do have an influence. The last thing we'll look at with classification is developing something called a confusion matrix, which is a visualization that allows us to understand the correct and incorrect classification of our model. Here, there's a function which I'll create, which is going to be what we're going to use. We're going to call this function to create confusion matrices. We'll make our first confusion matrix using the data output. And what is a matrix that here you can see the numerical representation. And what it is that on the diagonal, you have basically what's considered a good prediction. So you have the true label on the left, on the y-axis, the predicted label on the x-axis. And anything on this diagonal from left to right is considered accurate. It's hard to see here because this is an unnormalized, it's without normalization. But if we run it again with normalization, meaning that it's taking into consideration the number of samples in each of the classes, what you end up with is a visualization which is a little more interesting to look at. And what it's really telling you is that the true label, for example, here on the y-axis, is spread across the predicted labels. In our model, quite a large percentage of the zero values, this sort of like thermally neutral value, is predicted to be thermally neutral, but in reality is either very cold or very warm or somewhere in between. Here you can see that the diagonal is a little bit more prominent here, but you do see that there's a lot of misclassifications. The true label is very cold when the predicted label is only slightly cold. So this just gives you a sense of what was classified properly between the true label and the predicted label. It's just another version of seeing how the classification model worked. Congratulations, you've made it to the end of this. This is, like I said, is really the fundamentals of, just a very simple example of both regression and classification into data sets that you're familiar with from previous sections and that are from the building industry.